So in this lecture we are going to go further with our definition of higher order shape functions for two-dimensional problems. So remember we were working with the triangular elements. So here how do I construct a higher order approximation that is an order greater than 2 for a triangular element. So what we do, again the same thing that we had been doing as before. Here are the corners of the master element. So what we had said is that given the order, the shape functions should become the one-dimensional shape functions that we had seen earlier when I project them on a given edge of the triangle. So if this is my node 1, node 2, node 3, if I am talking of this edge, the first edge connected to nodes 1 and 2, then if I am talking of a p equal to 3 approximation, a cubic approximation, that approximation or those functions should become the one-dimensional cubic shape functions on this edge. So the one-dimensional cubic shape functions correspond to, in terms of the definition, the Lagrangian functions correspond to these 4 points on this edge, that is these 4 equally spaced points. This point will correspond to the coordinate 1/3 0, this will correspond to 2/3 0, and this is 1 0. Similarly on this edge again I should have the 2 equally spaced points, the 4 equally spaced points, okay, given by these locations. Here the coordinate will be essentially psi is equal to 2/3, eta is equal to 1/3, while this one will be psi equal to 1/3, eta is equal to 2/3, because psi plus eta has to be 1 here. Again I come to this edge, here I will have the 2 more points which are given by eta equal to 2/3 and eta equal to 1/3. So you see that I have made 1, 2, 3, 4, 5, 6, 7, 8, 9 points. Now for p equal to 3, from the Pascal triangle we had drawn earlier, we had said that for completeness we need p plus 1 into p plus 2 by 2 number of monomials. This for p equal to 3 is equal to 10. So 9 points means 9 definitions of Lagrangian shape functions. We need one more, okay, to give us 10 independent basis functions. So here how do I do things? So we do this, that let's say that I connect these points by straight lines, let's say, okay, and if I have drawn everything correctly, this should pass through like this. Now what happens? So what I have done is I have connected these points by a straight line, these 2 points by a straight line, and then I draw straight lines parallel to the 3 edges. So you see that if I look at these straight lines, they intersect at an interior point, okay. This interior point will have a coordinate, if you see it lies on the line eta equal to 1/3 and on the line psi equal to 1/3. So it will have a coordinate 1/3, 1/3, okay, fine. This is nothing but the centroid. So this point is another node for us. This becomes the 10th node. So our shape functions are now defined. Now I am going to color the nodes as with respect to these 10 nodes. And I'll follow some numbering scheme. Let's say this is 1, this is 2 as far as the definition of the shape functions is concerned, this is 3, this is 4, this is 5, this is 6, 7, 8, 9 and 10, okay. So I need 10 cubic basis functions in order to have a complete set which can completely represent any cubic polynomial, okay. So how do I now go about defining the shape function? So let's say that I would like to define n1 as a function of psi and eta. This will be what? So this function, the n1 is with respect to this node, okay, such that n1 is 1 at the node with coordinates 0, 0 and 0 at all other nodes. So how can n1 be a cubic polynomial in terms of psi and eta and vanish at all other nodes barring my node 1? Okay, so I'll put n1 as psi, and you see that here if I take my n1 to vanish on this line is nothing but the line psi plus eta is equal to 1/3. Make it vanish on this line, which is the line psi plus eta is equal to 2/3, and on this line, which is psi plus eta is equal to 1. So if I choose my n1 to vanish on these three lines, then automatically my n1 vanishes on all other nodes barring the first node. So how do I give a definition for that? We have done this in the previous lecture. So I will say it will have to vanish on the line psi plus eta equal to 1/3, so psi plus eta minus 1/3. It has to vanish on the line psi plus eta equal to 2/3, so psi plus eta minus 2/3, and it has to vanish on the line psi plus eta equal to 1, so psi plus eta minus 1. This is going to give me my n1, such that n1 hat at the point 0, 0, which is the first point, is equal to 1. This is equal to c into all these things. Okay, so it's quite easy. Here it will be minus 1/3, here it will be minus 2/3, and here it is going to be minus 1. So you can see implies c is equal to minus 2 by 9, so it is minus 9 by 2. So it's quite easy to find the definition of the first shape function. Similarly, if I want to find n2, n2 is a function which is 1 at this point and vanishes at all other points. Now if it has to vanish at all other points, we'll play the same game. It simply means that it has to vanish along this line, vanish along this line, vanish along this line, and vanish along this line. Okay, so if I am talking of n2, n2 is now written in terms of equation of this line. Equation of this line is psi is equal to 2 by 3. Equation of this line is psi is equal to 1 by 3. Equation of this line, which is psi equal to 0. So my n2 is very easy. n2 hat, which is a function of psi and eta, is, let's say, some constant d. It has to vanish on the line psi equal to 0, so psi minus 0. On the line psi equal to 1/3, so psi minus 1/3. On the line psi equal to 2/3, which is psi minus 2/3. This is it. Okay. So I can easily form n2. If I have to talk of n3, n3, if you see, vanishes on this line, vanishes on this line, and vanishes on this line. The equations of these lines are eta equal to 0, eta equal to 1/3, eta equal to 2/3. Okay, and it should have a value 1 at the node 3. So n3 will be some constant e into eta minus 0, eta minus 1/3, and eta minus 2/3. Okay. What about n4? If I have to find n4, you see n4 has to be 1 at this point and 0 at all other points. So if n4 has to be taken to be 0 on all other points, which means that n4 has to be 0 on this line, it has to be 0 on this line, and it has to be 0 on this line. Equation of this line is psi equal to 0. Equation of this line is psi plus eta is equal to minus 1. Equation of this line is psi plus eta equal to 2/3. With that I can actually construct N4. Okay, let's say that I want to construct by the same token N8. N8 will be 1 at the point 8 at the node 8, and it should be 0 at all other nodes, which means that it has to be 0. If I take it to be 0 on this line, 0 on this line, okay, which takes care of all these nodes, and 0 on this line. Then N4 is taken, this guy is taken care of. Okay. Similarly, I can define N10. Let's say N10, if it is, N10 is easy, it has to vanish on the 3 edges of the triangle. So if I have to talk of N10, N10 will be 0 along this line, which is eta equal to 0, 0 along this line, which is psi equal to 0, 0 along this line, which is psi plus eta equal to 1. So maybe I can write N10 is a function of sine eta is equal to something f into psi minus 0 into eta minus 0 into psi plus eta minus 1. So I can construct this way all the shape functions that we need in the master element. Okay, if I want to now go to p equal to 4, p equal to 4 will require, by our definition of p plus 1 into p plus 2 by 2 monomials needed to define a 4th order polynomial, this will require 15 shape functions to be defined. Okay. So let me also give some notations. These corner degrees of freedom are called the vertex degrees of freedom. These degrees of freedom on the edge are called the side degrees of freedom, and this interior degree of freedom, which is the 10, is called the interior degree of freedom. And look at 10. 10 is only non-zero in the given element. Okay, it is going to be 0 outside this element. So 10 is called an internal bubble function, while these edge functions, if you see, they are going to be non-zero only in the 2 elements which share this edge. Okay, so these are called side bubble functions. And while the vertex functions, well, they are non-zero in all the elements which have this vertex as a common vertex. Okay. So if I have to do the p equal to 4 case, let's go ahead and see how we are going to do it. Okay. So we will make these vertices. Now again, as we had done earlier, these shape functions, when I project them on the edges of the triangle, they should become equivalent to the one-dimensional 4th order shape functions on this edge. Now one-dimensional 4th order shape functions we had defined in the 1D case. They are given by specifying 5 equally spaced points on the line, p plus 1 equally spaced points. So I have these 3 points here. Okay, then I will have these 3 points here. Similarly, the 3 points here on these edges. So if you count all these points, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So as far as the vertex and edge functions are concerned, or the side functions, there are only 12. So I need to have 3 more functions which are now internal bubbles. How do I find them? Very easy. We connect these points with straight lines on opposite edges. Okay. Now I do this. Then you note that I have these, in this grid I have constructed these additional internal points. So what I do now, I define my shape functions for all these points. There are exactly 3 internal points, so no problem. I now have 15 points with respect to which I define the shape functions. Okay, so here I have 15 nodes. Okay, for definition of shape functions. And then I follow the same procedure as before to define these shape functions. For example, if I have to find the shape function corresponding to this one, let's give the numbering 1, 2, 3, this is 4, 5, 6, 7, 8, 9, 10, 11, 12, that's it, 13, 14, 15. So let's say I'm interested in the 11th one. The 11th one should be such that it is 1 at this point and 0 at all other nodes. So how can I choose 4 lines such that the 11th shape function vanishes on all other points? So I can choose maybe this point, this line, I can choose this line, I can choose this line, and I can choose this line. So my shape function should vanish on this line, on this line, and this line, and this line. So now looking at the equations of these lines, multiplying them together, I will get the 4th order shape function corresponding to the 11th point. Okay, so I can keep on constructing the higher order approximations to any order that I wish by using this kind of a structure, and it is quite easy. It can be done in the master element and immediately used. Okay, so in principle now we are in a position to construct any triangular Lagrangian basis function of any order that we wish to obtain. And the beauty of these basis functions are that you have exactly the number of functions that you need to have a complete definition of the polynomial of the given order. Now we are going to go to another family of shape functions or basis functions which are very popular, and in fact maybe they are used more than the triangles. So let's look at rectangular elements. So instead of meshing my simple domain that I had taken earlier, this rectangular domain, instead of meshing it with triangles, I could have meshed it with quadrilaterals, or with rectangles, okay, such that the size here is h1, the size here is h2. Okay. So let's take a generic element here, or now this is my element 1, this is 2, 3, 4. So the rectangular element will have 4 corner nodes or 4 corner vertices. Okay. Now everything has to be done or defined with respect to these corner vertices. So what is the simplest thing we can do is, let's take a generic rectangular element. For simplicity I am taking the first one. I will give a coordinate axis here, x and y, such that the first node has point locations 0, 0. This is the first node, second node, third node, fourth, fifth, sixth, seventh, eighth, ninth. So now I take these 4 nodes. So I'll have 1 for the element, 2 for the element, 3 for the element, 4 for the element. Okay. So I am taking the first element, and by 1, 2, 3, 4 here I mean the local numbering, just like we did for the triangles. So the coordinates here are going to be 0, 0, h1, 0, h1, h2, and 0, h2. You see, again I am doing a counterclockwise numbering. So what is the simplest basis functions that we can define, or simplest element shape functions? They have to be defined with respect to these 4 vertices. Okay. So those shape functions, if I define now, how am I going to do that definition? So the definition is very simple. Let's now take this element apart, because these angles are 90 degrees. So let's imagine I have taken these two edges apart, this edge and this edge. Let's say this edge with the nodes 1 and 2 and this edge is with the nodes 1 and 4. On each of these edges, as we had said for the triangles also, the shape functions should be such for the 2D domain that the projection on the edge becomes the 1D shape function. So let's take now the same principle here. We have to define the shape functions in such a way that the projections on the edge become the 1D shape function. So on this edge it will become this 1D shape function. These two, let's say, linears. So I'll say this is n1 of x, this is n2 of x. Similarly, here I will have these functions. This will be n1 of y and this will be n2 of y. Okay. So on each of the edges I have defined the linears. Okay. What is n1 of x? As a function of x on this edge, it's quite easy to define this shape function. It should vanish at this point. It should be equal to 1 here. So I will define it as h1 minus x divided by h1, or which is 1 minus x by h1. The second one, n2 of x as a function of x, because these are one-dimensional shape functions and along this edge there will be only functions of x. This will be equal to nothing but x by h1. Okay. Similarly, n1 of y is equal to, from what we have done, n1 of y should be 1 here, 0 here at the point y equal to h2. So by the same token it becomes 1 minus y by h2 and n2 of y becomes y by h2. Okay. So this is a simple definition. Now using these functions, these 1D shape functions that we have defined along this line and along this line, what I am going to do is take product of these functions to get all the functions. You see why it's going to work. If I take the product of n1x, that is the function on this line corresponding to this node, it is n1x. Function on this line corresponding to this node is n1y. So if I take the product of n1x and n1y, by the definitions of n1x and n1y, this function is 1 at this node and vanishes at this node, which means that it vanishes at this node also. Okay. So it satisfies all our constraints that the function should have a value 1 at this node and 0 at all other nodes. Similarly, I go to this node. This node lies as a second node on this line, so I take n2 of x. Okay. On this line, this is the first node, so I take into n1 of y, and by definition this n1 of y is going to vanish here and here, n2 of x is going to vanish here, so it vanishes at all other points and gives me a value 1 at the second node. So if I take this kind of product, so n3 of x, I say it lies actually as a second node of this line, so n2 of x, and it lies as the second node of this line, so n2 of y. So n2 x into n2 y, it should do the job. And the fourth one should be n1 of x into n2 of y. So we are going to define our shape functions now in terms of this. So n1, which is a function in the element x and y, in the element 1, I'll say, is equal to n1 of x, which is a function of x, into n1 of y, which is a function of y. n2 in the element 1 as a function of x and y is equal to n2 of x into n1 y. n3 in element 1 is equal to n2x, which is a function of x, into n2y, which is a function of y. And n4 in element 1, which is a function of x and y, is equal to n1 of x and n2 y. Okay. So I have defined these 4 shape functions with respect to the 4 vertices of the rectangle, and this is the minimum we can do, okay, because these functions have to be defined by the logic that we have been following with respect to these 4 vertices. Now you see that these are by definition product of functions in the x direction and functions in the y direction. Since they are defined as products of functions, 1D functions defined in the x and y direction, they are said to be tensor product family of shape functions. Let us look at some features of it. What is my n1 of x? It is nothing but 1 minus x by h1. n1 of y is 1 minus y over h2. So if I take this product, this is going to be 1 minus x by h1 minus y by h2 plus xy by h1 h2. So see, this part is the linear part. This is linear. It is linear in x and y. This part is actually bilinear. That is, it is not linear, it is more than linear in x and y. So what do these basis functions, the shape functions do is, they seem to represent more than the set of functions we need to represent completely to define a linear. That is, they contain more terms than just the linears. So let's go back. We had the Pascal triangle here, 1 x y x squared xy y squared x cubed x squared y xy squared y cube. I will write up to the 4th order, x4 x cubed y x squared y squared xy cubed y to the 4th. So what will happen if I go and expand all of these functions n1, n2, n3, n4, I will find the same feature, that they will contain the linear part, that is in terms of 1 x and y, plus they will also contain the product of x and y. So if I come to the Pascal triangle, what happens is, if I look at the representation of these functions, they will not only represent the linear, they will also contain the xy part. Okay, that is more than what was really required to define the linear polynomials. Similarly, if I now go and define, if I want to define now the quadratic shape functions. So how do I define the quadratic shape functions? I will simply add on each of these edges here, for example, the intermediate points. Okay, so on these edges, so if you see all these edges together, they will comprise again we connect these points just like we had done for the triangles. So I will get an additional node in the middle. So you will see that there are 9 such functions, which is product, because we are talking of products, 3 functions on this edge, 3 functions on this edge, 3 into 3 I have 9, and these 9 functions are nicely given here in terms of these nodal values. Okay, so if I have to now give these 9 functions in terms of the quadratic, I will define the quadratic shape functions on the edge and multiply for the 2 edges to get the quadratic shape functions for the element. So here you see that the feature is that it is actually, I get p plus 1 functions in one direction into p plus 1 functions in the other direction. That is, I will get p plus 1 squared functions. So for the linear I had 2 into 2 4, For the quadratic, I will have 3 into 3, which is 9. For the cubic, I will have 4 into 4, which is 16. So I'm increasing the number of functions as I'm increasing the approximation. Okay. So what will happen if I go and look at the quadratics by the same formula that we have followed, the same line of approach? Okay, you'll see that the quadratics should be representing this much to be complete, but it turns out they not only represent this much, they go and represent this whole set. That is, the quadratic definition will include all these functions. It will go beyond the quadratic and have these extra functions. So this way, you see that I am carrying on by this definition of these shape functions, these additional functions also in the representation above the requirement of completeness. Okay, this is a feature of the tensor product family. And now the question is, okay, not always will I have such a nice rectangular domain. So what do? I would like to take this kind of a domain. In this domain, the mesh that is going to come out, if I try to mesh this domain with 4 noded entities, this mesh will have quadrilaterals. So it will be a mesh of quadrilaterals, not of rectangles. Okay. So when I have a mesh of quadrilaterals, what do? Then we do not have this luxury of having these two perpendicular edges based for which we define these individual functions, take the product. I cannot do anything at the physical level, that is at the level of the physical element. So for that, I'll have to map this. What we do is we map this physical element to a master element. So we'll have to define the master element now for these quadrilaterals. Okay, and we define now the master element in such a way that I can use this tensor product representation to get my shape functions in the master element. So let's do that. So this is, let's say, my physical element, which is a quadrilateral. Okay, which has n nodes x1, y1. It's a generic quadrilateral x2, y2, x3, y3, and x4, y4. What we are going to do, so let's say I have the xy coordinate system somewhere, x, y. We are going to take it to a master element which is defined as this. This is psi, this is eta, this is the node 1 in the master element, node 2 in the master element, node 3, node 4. So this is my generic element tau, this is the master element tau hat. And this was my node 1 in the physical element, node 2, node 3 and node 4. This node 1 will have coordinates minus 1, minus 1. Node 2 will have coordinates 1, minus 1. Node 3 will have coordinates 1, 1, and 4 will have minus 1, 1. So I have these in the master element. Our these 1, 2, 3, 4 nodes, they map to this one. I can call it 1 hat, 2 hat, 3 hat, and 4 hat nodes with these coordinates. And you see that this master element is now a square. So this is called a master square. Now, how do I define the shape functions with the master element? Very easy. That again, now I take, see, you see the master element has edges which are perpendicular to each other. So I will take these edges out. with the nodes 1 hat, 2 hat, 1 hat and 4 hat. And then on these edges I can redo the whole job as I had done earlier, that I will define, let's say if I am talking of the linears, I will define these linear functions on this edge which is in the direction psi, this edge which is in the direction eta. I will define again these linears. So I will say that this is n1 psi, this is n2 psi, this is n1 eta, this is n2 eta. Okay. So this way now I can define these 1D shape functions on these two, the psi edge and the eta edge. And in terms of the products of these 1D shape functions, now I can define the shape function for the master element. So now if I have to define the bilinear or the linear approximation, it's generally the approximations, because it's a tensor product, it's called bi-p approximation. Okay, which means it's p in one direction and p in the other direction. So it's a product of these two p's. So I will say the bilinear, when p is equal to 1, it's called a bilinear approximation. n1 hat, which is a function of psi and eta, will now be nothing but n1 psi into n1 eta. n2 hat as a function of psi and eta is equal to n2 psi n1 eta, and n3 hat, which is a function of psi and eta, is n2 psi n2 eta. n4 hat psi and eta is equal to n1 psi into eta. So now we can define the bilinear shape functions here, which are, here it's very easy, it will turn out to be 1/4 of 1 minus psi into, it will be 1 minus eta. Okay, this one will be 1/4 of 1 plus psi into 1 minus eta. This one will be 1/4 of 1 plus psi into 1 plus eta, and this will be 1/4 of 1 minus psi into 1 plus eta. So this way I can define the bilinear shape functions for the master element. Similarly, so these are bilinear shape functions. Similarly, I can go and now define the quadratic shape functions, biquadratic shape functions. So let's also look at the biquadratics. So here, as we had done earlier, this is my psi edge, this is my eta edge. So on these edges I'll add these additional nodes on the edge, which is at the mid side, and I'll define these 1D functions on the edge, which is very easy to define. 1D quadratic functions. This becomes n1 psi, this becomes n2 psi, this becomes n3 psi. On the eta edge, I'll similarly define n1 eta, n2 eta and n3 eta, n1 eta, n2 eta and n3 eta. So I have 3 functions on each edge, so I should have now these 9 functions defined on the master element with respect to these 9 points. Like this. I'll call this point 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, 9. Okay. So again, depending on the point which lines it lies on, I will find the corresponding shape function. Like for example, n1 hat as a function of sine eta should be equal to, it lies on the first point, it has the first node of the psi side, first node of the eta side, so it should be n1 psi into n1 eta. Similarly, n2 hat, it lies on the third node of the one side of the psi side and the first node of the eta side, so it will become n3 psi into n1 eta. If I need to define now n3 hat, it becomes n3 hat lies on the third node of the psi side and the third node of the eta side, so n3 psi, n3 eta. Okay, n4 will be n1 psi into n4 hat is equal to n1 psi into n3 eta. Similarly, n5 will be, see, it's a second node for the psi side and first node for the eta side, so it will be equal to n2 psi into n1 eta. Let's say that I want to continue this, I want to get to n9 hat. n9 hat is equal to, it lies on the second node of the psi side, second node of the eta side, so it becomes n2 psi n2 eta. So I am able to define all the 9 basis functions with respect to these definitions, and these definitions of n1, n2, n3 and so on, depending on the p on the edge, we have already discussed it in the 1D definitions. Okay. Similarly, I can construct bicubic approx. So here, if I look at the master element, I will have these corner vertices. Now on this edge, I will have 2 more equally spaced points, just like we had done also in the triangles. Okay, so equally spaced points, and then connect these by lines. Okay, so you'll get 4 more points lying in the interior, and so you will get a grid of 16 points. So bicubic will have 16 functions. So we can continue this to whatever order we want. Okay. So constructing these basis functions in the generic quadrilateral element has to be done at the master element level, and we follow the same principle that we had followed for the rectangular element, and we get the shape functions. Question is, will it give me a continuous approximation? Answer is yes, because if I have the next element sitting here, so if I have 2 elements like this, on this edge, if I look at that, on this edge, both these elements, the shape functions should become equivalent to the 1D shape function on the edge. Okay, so both these functions on this edge from either side are going to match, because they have to become equivalent to the same 1D shape functions. So because the functions match, so the approximation is going to match. Okay, so as far as continuity is concerned, that's not a problem here in this definition. Another question. Okay, we have not discussed how we map this quadrilateral to the master element. Okay, what kind of mapping is it, which gives me this? So the mapping, you see that this is a domain with straight edges, going to a domain with straight edges. So here for the mapping of the geometry, in this case, as long as I do not have curved elements, we are going to use bilinear. I.e., x at any point sin eta here in the master element will be sum of I is 1 to 4 xi mi. I am deliberately writing it as mi as a function of sin eta. Y as a function of sin eta is sum I is 1 to 4 yi mi hat sin eta. Okay, where are these xi yi's? This is the xi yi, which is x1 y1 x2 y2 x3 y3 and x4 y4. Now why I have written mi? Because I want to bring it out very clearly that the mapping need not always be of the same order as the approximation. Okay, here irrespective of whether I am using a cubic approximation or a fourth order, that is bicubic or quartic or biquadratic, my mapping is always going to be bilinear for this kind of a domain, where a quadrilateral is a straight edged quadrilateral. Okay, so the mapping should always be done with respect to the bilinear shape functions, while my approximation can be done with respect to any shape functions that I wish. Okay, so these mi's are nothing but the bilinear shape functions. So let's now see that as far as our computations are concerned, finally we want to put everything in a computer program. So as far as the computations are concerned, we need quantities like del x del psi, del x del eta, del y del psi, del y del eta, because we have mapped all our functions from the physical domain to the master domain. So why not do all the integration and other procedures which are required to get the stiffness matrices and the load vectors in the master element. Okay, so these quantities are required. How do I find these quantities? So if I see that x, if I write it, will be equal to x1 into 1/4 of 1 minus psi into 1 minus eta, plus x2 into 1/4 of 1 plus psi into 1 minus eta, plus x3 into 1/4 of 1 plus psi into 1 plus eta, plus x4 into 1/4 of 1 minus psi into 1 plus eta. Y is also written similarly in terms of the y. So these are our mi's, m1, m2, m3, m4. Okay. So del x del psi becomes equal to, from what we have done, minus x1 into 1 minus eta by 4. Here plus x2 into 1 minus eta by 4, plus x3 into 1 plus eta by 4 minus x4 into 1 plus eta by 4. Okay, so this one will be equal to, if I write it in terms of sin eta, 1/4 of, collect all the constant parts, x2 minus x1 plus x3 minus x4 plus x2 minus x1 plus x3 minus x plus eta into x1 minus x2 plus x3 minus x4. Okay. Similarly, del x del eta is equal to, you will have minus x1 into 1 minus psi by 4 minus x2 into 1 plus psi by 4 plus x3 into 1 plus psi by 4 plus x4 into 1 minus psi by 4. Okay. So if I collect, it will be 1 by 4. I want to collect here itself. It will be equal to x3 plus x4 minus x1 minus x2 plus psi into x1 minus x2 plus x3 minus x4. Okay. Similarly, now I can get the quantities corresponding to y by replacing this guy by y and replacing here by y1 and y2 and so on. Okay. Similarly, this one I replace by y and these are by y1, y2 and so on. So del x del eta, del x del psi, del x del eta, del y del psi, del y del eta can be now obtained. Once I have obtained these quantities, why do I need them? I want to use them to get the matrix of the transformation. Okay, that is, I would like to write dx dy is equal to del x del psi del x del eta psi del y del eta into d psi d eta. Okay, and if I go back and look at this one, I can write this expression as something like a1 plus a2 eta, and this expression as, if I can squeeze it in somewhere, this expression becomes b1 plus b2 psi. And what we'll do is, we'll say this one is going to be c1 plus c2 eta, and this one is going to be d1 plus d2 psi. Okay. So if now I have to compute the Jacobian, because Jacobian is needed for the transformation of the integrals from the physical domain to the master domain, this will be equal to del x del psi into del y del eta minus del x del eta into del y del psi. Okay. So by what we have done, our del x del psi is a1 plus a2 eta. This one is d1 plus d2 psi, where the d1 d2 are again obtained from the previous expression. This one is del x del eta is b1 plus b2 psi, and the second one is going to be del y del psi is c1 plus c2 eta. So you see, in the product, what do I get? It will be something a1 bar plus a2 bar psi plus a3 bar eta plus a4 bar psi eta, where these bars are obtained by this product. For example, a1 bar is a1 d1 minus b1 c1 and so on. So you see what happens. The bottom line is that the Jacobian is no longer a constant. Okay, even with this bilinear map, this is no longer a constant because it is now a function of psi eta and the product psi eta. While in the triangular element, when we did the linear map, which we had discussed, the Jacobian turned out to be a constant. Okay, So when I am going to do the integration, the numerical integration and so on, I have to account for this part of the Jacobian. Okay, the Jacobian is also a bilinear in terms of the sine eta, and because it's a bilinear in terms of sine eta, we would like, as such, the Jacobian should always be greater than 0, because that's what's physical, that a positive area maps to a positive area. It's not that the area can become negative, okay, or a given area cannot map to a point, not allowed. Okay, so an area will map to another area, but this will be a positive number. The ratio will be maybe less than 1, greater than 1, but nevertheless it's a positive number, and the ratio of the two areas is nothing but the Jacobian. When we say the Jacobian is 0, which means the area maps to a point, which we are not allowing, we cannot have, it's unphysical. So we would like to avoid elements, geometries of quadrilaterals for which this Jacobian can become a negative or 0 at a point. Who stops this from becoming negative or 0? I can have some combinations of sine eta given this a1, a2, a3, a4, that is the 4 nodal coordinates will define what are these a1 bar, a2 bar, a3 bar, a4 bar, okay, in such a way that the Jacobian could be negative at a point. Okay, it's quite easy to show that this can only happen when, let's take this as the initial physical element. Let's say that I have 1, 2, 3 and 4, these 4 points, and I decide to start moving this point inwards, point 3 inwards. It will turn out that point 3 could lie on a triangle, okay, a degenerate triangle. Now if I go beyond this, okay, that is if point 3 moves to this point here, then the Jacobian will be negative at some points. That is, such geometries of quadrilaterals are not allowed for which one of the angle becomes an obtuse angle. Okay, so should not allow those geometries for which one of the angles is an obtuse angle. This is not allowed. So one has to be very careful when making the mesh that I do not get this kind of a quadrilateral domain. We can always convert it into two quadrilaterals for which the quadrilateral is convex, that is the angle is, well, certainly less than equal to 180 degrees. We do not want quadrilaterals for which angles are large. We should not have this kind of quadrilaterals, large or very small, such needle shaped quadrilaterals. Generally their performance will be pretty bad. So while making the mesh, we have to ensure that these quadrilaterals are as good as possible. The angles are not too large, the angles are not too small. Okay. In this case, we will have a point where Jacobian is less than equal to 0 for some psi and eta. So this is a very important point that has to be kept in mind when we are using quadrilateral elements. Okay. Now here we have said that look, as far as the definition of the quadrilaterals is concerned, these rectangular elements, we have overdone the job. That is, we have in the Pascal triangle, we have actually accounted for more terms. Now the question is, can we redefine our basis functions over the quadrilateral, or the shape functions over the quadrilateral, in such a way that we do not overdo the job? That is, can we cut out some of these extra terms? The answer is yes. That comes by using what we call the serendipity family of functions. That is, completeness is guaranteed and these extra terms are cut down. Okay. So in the next class, as far as the approximation is concerned, we are going to discuss the serendipity family of shape functions. Then we are going to now consolidate everything in terms of the finite element approximation in an element, okay, and then we'll move on to look at how are we going to use this in a computational regime. That is, how do we do numerical integrations for the quadrilateral or for the triangular element.